Chapter 9, Radicals and Complex Numbers. This is Section 3, Adding and Subtracting Radical Expressions. Similar to adding and subtracting polynomials, where when we add and subtract polynomial expressions, we combine like terms. Here we will discuss adding and subtracting radical expressions, where we will combine like radicals. That is a radical expression that has the same root and the same radicand. Like radicals share the same root and radicand. Here we will learn to use the distributive property to add and subtract like radicals. In other words, we will combine the coefficients. Also, we will use radical expressions in application problems. Again, as we've seen previously, the Pythagorean theorem, a squared plus b squared equals c squared, where if we solve for either of the legs a or b, or if we solve for the hypotenuse c, this would involve us taking a square root on each side of the equation, thus using a radical in an application problem. Two or more radical expressions are called like radicals if they have the same index and the same radicand. For instance, the expressions square root of 2 and 3 square roots of 2 are like radicals. Think about how we're saying that. How many square roots of 2 do you have? The first expression, 1 square root of 2. The second, 3 square roots of 2. Thus, if you were to combine using addition, how many square roots of 2 do we have? We have a sum or a total of 4 square roots of 2. We combine the square roots of 2 by adding the coefficients, the understood 1 for the square root of 2 and the 3 for 3 square roots of 2. 1 plus 3 gives us 4, thus we have 4 square roots of 2. However, the expressions square root of 3 and cube root of 3 are not like radicals. As you see there, the first radical expression has a root of 2. The next expression has a root of 3. The roots and the radicand, and another word for root is index. Thus, the root and the radicand must be exactly the same. Here, the radicand of 3 is the same, however, the root of 2 and 3 are not. Two radical expressions that are like radicals can be added or subtracted by adding or subtracting their coefficients. It is important to realize that the expression square root of a plus square root of b is not equal to the square root of a plus b. Notice here that a and b are different radicands. The square root of a, although it is a square root indicating a root of 2, the root of 2 for the square root, however, the radicand of a. The second expression, root of 2, radicand b. The radicands are not the same, thus we cannot combine those two expressions. So for example, you may be tempted to add the square root of 6 plus the square root of 3 and get the square root of 9, but remember you cannot add unlike radicals. So the square root of 6 plus the square root of 3 are unlike radicals and they cannot be combined any further. You would leave it simply as such. We'll look at some examples here for parts A, B, and C. It says simplify each expression by combining like radicals. We will see for each of the three expressions here, we have the sum and difference of terms, where each of our terms here, the things that are being added and subtracted together, each involve radical expressions. It is up to us to determine which radical expressions share the same index in radicand, in other words, the same root in radicand, and we can combine their coefficients using addition and subtraction. With part A, 1 square root of 7 plus 5 square roots of 7 minus 2 square roots of 7. Notice for part A, the coefficients are 1, 5, and negative 2. Which of these three radical expressions are like radicals? Note for all three of these radicals, their roots are 2, they are square roots, and their radicands are all 7. Thus, for part A, we can combine all three terms into one single term. How many square roots of 7 do we have? Part A, we have 1 plus 5 minus 2 square roots of 7. So to look at our first objective for this section 3 here, using the distributive property to combine like radicands or like radicals, for part A, combining the coefficients 1 plus 5 minus 2. So in other words, if you were to take the square root of 7 that is common for all three terms, factor it to the right here. This is our right distributive property. If we move that square root of 7 to the right and introduce parentheses, what do we leave behind? We leave behind our coefficients, the positive 1, positive 5, and negative 2. So how many square roots? Well, we had one of them. We added 5 to get 6, and then we subtracted 2 to get 4. We have 4 square roots of 7. Four square roots of 7. For part B, 6 square roots of x, subtract 1 cube root of 4, subtract 5 square roots of x, plus 2 cube roots of 4. So for part B, we have 4 terms. They are all radical terms where we have the square root of x and the cube root of 4. Notice here we have 2 different types of radicals. We have a square root radical and a cube root radical. We cannot combine these using addition or subtraction because they are not like radicals. However, for these 4 terms here, 2 of the 4 are like radicals and the other 2 are like radicals. For part B, 2 of the terms have the square root of x. We start off with 6 square roots of x, but we are to subtract 5 square roots of x. So how many square roots of x do we have? We can show this using our distributive property, but of course, if you already have that idea, 6 minus 5 is 1. Thus, we leave behind 1 square root of x. And we can write 1 square root of x as the square root of x. But what are we going to do with those other 2 terms here? We have a minus cube root of 4 plus 2 cube root of 4. The root of 3 and the radicand of 4 are the same, thus these 2 terms are like radicals. A minus cube root of 4 plus 2, this is a minus 1 plus 2, minus 1 plus 2 is a positive 1. So we have plus 1 cube root of 4. And we would write that without the coefficient and just put plus cube root of 4. So what do? We simplified our 4 radical terms down to 2 radical terms. Square root of x plus cube root of 4. These 2 terms cannot be further combined because the roots are not the same, nor are the radicands the same. Thus, we leave our simplified expression as the binomial square root of x plus cube root of 4. With part C, we start off here with 3 cube roots of x plus 2 cube roots of x plus 1 square root of x minus 8 square roots of x. So for part C, we have 4 terms. All 4 terms have a radical. Which of these are like radicals? The first 2 terms are like radicals because they share the same root of 3 and radicand of x. Thus, how many cube roots of x do we have? We start off with 3, but we add 2 cube roots of x for a total of 5 cube roots of x. Adding the coefficients 3 plus 2 for a total of 5 cube roots of x. How many square roots of x do we have? Well, the plus square root of x indicates we have a positive 1. So we have 1 square root of x, but we subtract or take away 8 square roots of x. 1 minus 8 is negative 7. Thus, we have minus 7 square roots of x. Looking at what we have here, our 2 terms we have left over here, we combined 4 terms and simplified down to 2. Our remaining 2 terms here do not have the same root. However, notice here their radicands are the same, right? We have the same radicand, however, this is a cube root, and this does not have a number indicating a square root. The roots are not the same, the index or the root is not the same. Thus, we cannot combine our 2 terms down, and we have our simplified binomial expression. For exercises 1 through 6, combine the radical expressions if possible. For exercises 1 through 6, we are either adding or subtracting radical terms. For number 1, 3 square roots of 2 minus square root of 2. A number not in front of that square root of 2 indicates a 1. So this is 3 square roots of 2 minus 1 square root of 2. The radicals are the same. That is a square root radical, and 2 is our radicand. So we can combine these 2 terms here. 3 minus 1 for the coefficients gives us 2. Thus, 3 square roots of 2 minus 1 square root of 2 is 2 square roots of 2. course, this is 2 multiply the square root of 2. Number 2, similarly here, 6 square roots of 5 minus 2 square roots of 5. 6 minus 2 is 4, indicating we have 4 square roots of 5. For number 3, 2 square roots of 6 added to 5 square roots of 6. The square root of 6 for each of these here. Again, we can consider for number 3 the distributive property, because as you see there, the 2 for number 3 is multiplying the square root of 6. The 5 is multiplying the square root of 6. If we factor out, rather, the square root of 6, when we factor, introduce parentheses to determine what we leave behind, we leave behind a 2 and positive 5. Indicating here, 2 plus 5 gives us the 7 square roots of 6. Think about that like radical just like a variable. If we had 2x plus 5x, 2x plus 5x is 7x, because again here, square root of 6 as a factor, 2 plus 5 multiply the square root of 6, giving us our simplified 7 square roots of 6. Number 4, 3 square roots of 7 plus 2 square roots of 7. Our radical has an index or root of 2 and a radicand of 7. Thus, these are like radicals. We combine the coefficients for number 4. 3 plus 2 is 5, giving us 5 square roots of 7. For number 5, 8 square roots of 5 plus 9 cube roots of 5. As we see for number 5 here, our radicand is 5, our number or value under the radical. However, our first term is the square root of 5. That is an index or a root of 2. Our second term is the cube root of 5. That is an index or root of 3. The roots are not the same. Therefore, for number 5, our two terms are unlike radicals, and we cannot combine those two terms. Thus, for number 5, we leave our radical expression as the binomial eight square roots of 5 plus 9 cube roots of 5. For number 6, 3 cube roots of 3 plus 6 cube roots of 3. How many cube roots of 3 do we have? A total of 9 cube roots of 3. We see here for number 6, factoring out the cube root of 3, you leave behind here a 3 and positive 6. Thus, 3 plus 6 multiply the cube root of 3 gives us the total of 9 cube roots of 3. However, before concluding that two radicals cannot be combined, you should first rewrite them in simplest form. For the following exercises 1 through 6, we dealt with radicands 2, 5, 6, 7, 5, and 3 underneath the square root and cube roots. For each of these radicands, they cannot be further simplified. They are in their simplest form because there is no square factor or cube factor that lives underneath these square roots and cube roots, respectively. So for our next examples, we will see where we have examples of radicands that are not in simplest form. In other words, for those radicands under square roots, they may contain perfect square factors. For those radicands underneath cube roots, they may contain perfect third power factors, and so on. For part A, simplify each expression by combining like radicals. For part B as well. Part A here, we have the square root of 45 times x plus 3 times the square root of 20 times x. Note for our first term, our radicand is 45 multiply x. For the product of 45 and x as our radicand, we use the product rule of radical expressions, section 1 of chapter 2. The square root of 45 multiply the square root of x, as our product rule for radicals states here. The square root of a times b equals the square root of a multiply the square root of b. For our factors underneath the radical, we can rewrite each factor under its own radical. The square root of 45 multiply the square root of x plus 3 times the square root of 20x. 20 is multiplying x, thus we rewrite 20 under its own square root, and we rewrite the factor of x under its own square root. So our second term here, 3 multiply the square root of 20, multiply the square root of x. And now we will go to our full view here. For our first term, let's worry about simplifying just this term here, square root of 45 times the square root of x. We start with 45. Is it a perfect square, or does it contain a perfect square factor? We saw this example quite often in the last section. "45 can be rewritten as the product of 9 times 5, where 9 is a perfect square factor. Thus, using our product rule for radicals, the square root of 45 is the square root of 9 times the square root of 5. We evaluate the perfect square under the square root. Square root of 9 is 3. Question here now, can we simplify further the square root of 5? Can we simplify further the square root of x? 5 is a prime number. In other words, we can only write 5 as 5 times 1. 1 is a perfect square, but it doesn't help us simplify. Thus, the square root of 5 is as simplified as it gets. X is also a prime factor in that it cannot be further factored. X is one factor of x, and that's it. Because we cannot further simplify either of these radical expressions, we will then use our product rule to bring these two radicals together. The square root of 5 multiply the square root of x, just as we saw up here. If we can rewrite 45 as the product of the two radicals, then we can always take them and bring them back together into one radical. Here, we'll bring it together into the square root of 5 times x. Thus, for our first term began as the square root of 45x, so our radicand was 45x. Now you see here our simplified radicand for our term is 5x. What about our second term here? 3 multiply the square root of 20 multiply the square root of x. Well, 3 is just a factor there. It's a whole numbered factor. We cannot further do anything with 3. 3 is a prime number. It cannot be factored. But what we're dealing with here is this radical factor, square root of 20. 20 is not a perfect square. It's in between, however, 16 and 25. Thus, the square root of 20 is some irrational number between 4 and 5. 20 contains a perfect square factor, that is 4. Using our product rule for radicals and evaluating our perfect square, as we see here, all of our factors that are multiplying together, 3 times 2, and 3 times 2 is 6. The square root of 5 multiply the square root of x, just as we see over here, we will combine using the product rule. So our two terms here, 3 square roots of 5x plus 6 square roots of 5x. Note here that when we started with this example, our radicands were unlike. We could not combine our terms at the beginning of this problem. But through simplification using the product rule for radicals, we end up with a simplified radical term for each of the two terms, where each of the two terms now has a like radical. That radicand is 5x, and the root for each of these radicals is a root 2. This is the square root. So how many square roots of 5x do we have? Combining the coefficients, 3 plus 6. We have here 9 square roots of 5x. For part B, 5 square roots of x cubed minus x square roots of 4x. So let's think about that there. Our first term contains only the variable expression x cubed, that is our radicand. X cubed under the square root, if we recall back here, because we are working with the square root radical, any variable or variable expression that contains an even exponent is in fact a perfect square. However, if we have an odd number for our exponent, x cubed, x to the power of 3 is not a perfect square. However, it does contain a perfect square factor. Using the product rule for exponents in chapter 5, section 1, x cubed can be rewritten as x squared multiply x. Thus, using our product rule for radicals, the square root of x cubed is rewritten as the square root of x squared multiply the square root of x. We do this because our inverse property rule here states that the square root of x squared our exponent and our radical will cancel. In other words, what do you square in order to get x squared? You square the variable x. Thus, the square root of x squared is x. So how many square roots of x do we have here? We have 5x, square roots of x. So 5 multiply the square root of x cubed is 5 multiply x, multiply the square root of x. Subtract. X multiply the square root of 4x. 4 is multiplying x under the radical, so our product rule here. Breaking apart each factor under its own square root sign, we evaluate the square root of 4 and we get 2. So our second term here, x is multiplying 2, which is multiplying the square root of x. X multiplied 2 can be rewritten as 2 multiply x. We do this, of course, because for terms, with these radical terms that we have, the numerical factor is considered the coefficient, and that coefficient is written out front. How many x square roots of x do we have? We have 5x square roots of x. How many square roots of x do we have over here? Well, we have 2x square roots of x. So note again here that for polynomial expressions, we have to have the same variable raised to the same exponent. Here, it's the same concept here. We have to have the same variables and we have to have the same radical. And what is the radical again? It has to have the same root, which in this case is the square root. Both of these are square root radicals, so we're good there. And both radicands, expressions under the radical, are the exact same. They are the variable x. So how many square roots of x do we have? We have 5x, but we are going to take away 2x. So if we were to consider using that rule of radicals to the distributive property to factor out the square root of x, to the right here, introduce parentheses, we leave behind 5x minus 2x. What's 5x minus 2x? 3x. So we get a single term for part B. For part B, 5 square roots of x cubed minus x square roots of 4x simplifies down to 3x square roots of x. Looking at two numbers that are very familiar to us under the square root radical. For exercises 21, 22, and 23, combine the radical expressions if possible. For number 21, we see that these are unlike radicals. The radicands are not the same. We have 45 and we have 20. However, we need to check to see if we can further simplify these radical expressions. For 3 square roots of 45, as we saw in part A, square root of 45 is the square root of 9, multiply the square root of 5, plus 7 square roots of 20. And of course, 20 is 4 times 5, thus giving us the square root of 4, multiply the square root of 5. Evaluate the perfect squares. Remember up here, these are all factors that multiply together. 3 multiply 3, and 3 times, see, square root of 9 is 3. 3 times the factor of 3, this is going to give us 9 square roots of 5. 7 multiply 2 is 14, giving us 14 square roots of 5. Each of our radicals here have the same radicand, and they are under the square root sign, therefore their root is 2. How many square roots of 5 do we have? 9 plus 14 is 23, giving us 23 square roots of 5. Number 22, 5 square roots of 12 plus 16 square roots of 27. Twelve is not a perfect square. However, 4 times 3, exposing a perfect square factor for our radicand of 12, using our product rule for radicals. Now plus 16 square roots of 27. Of course, pause the video at any time to be able to work ahead so that I will not spoil all the fun. 3 factors plus 3 factors. Let's multiply out. Let's first evaluate. Square root of 4 is 2. Square root of 9 is 3. 5 is multiplying 2 to give us 10. So our first term here, 10 square roots of 3. 16 times 3, 16, 32, 48. 48 square roots of 3. Note here for our two terms, the radicand is 3. They're both under the square root, so our index or our root is 2. How many square roots of 3 do we have? Combining through addition, when you say how many, right? How many? A sum, a total? 10 plus 48 to give us 58 square roots of 3. We can see here that we are fully simplified because our radicand of 3 here cannot be further factored. According to section 2, chapter 9, 3 is a prime number dealing with a prime number. It can only be written as the product of 3 and 1. 1 is a perfect square, but it's not going to help us simplify our radical expression. If you have a radicand that contains a perfect square factor, you are not fully simplified. You must take that additional step further. Here we cannot. We are fully simplified. Number 23, we have 2 multiply the cube root of 54. So we have 2 cube roots of 54 plus 12 cube roots of 16. Now we can't combine here for number 23 because 54 and 16 are not the same radicand. However, they may be simplified in such a way that we can rewrite these in simplified terms such that their radicands are the same. Let's try it out. Let's try it out, man. Let's try it out. Number 23, 2 cube roots of 54. So we're switching it up. We're no longer working with square roots. We're not worried about things that are being squared. We're worried about things that are being cubed now. Is 54 a perfect cube? 2 to the power of 3 is 8. 3 to the power of 3 is 27. 4 to the power of 3 is 64. That tells us that if we take the cube root of 54, it's going to give us some irrational value between 3 and 4. Right? If you take the cube root of any number that is not a perfect cube, it is going to give you an irrational number. If you take the cube root of a perfect cube, it will give you a fraction or it'll give you a whole number. Or, of course, an integer because it can be negative. Should say it that way. Rational number. If you take the cube root of a perfect cube, you will get back a rational number. In other words, a fraction or an integer. If you take the cube root of a number that is not a perfect cube, for example, 54, try that out in your calculator, try it out, you will get an irrational number. So for 2 times the cube root of 54, this is always going to be an irrational value. Does 54, however, contain a perfect cube factor? Listing out those perfect cubes, 3 to the power of 3 is 27. 27 divides 54 twice. Using our product rule for radicals, even for cube roots, going to the full view there, 2 cube roots of 54. We rewrite that as 2 cube roots of 27 multiply cube root of 2 plus 12 cube roots of 16. 16 is not a perfect cube. However, 8 is a perfect cube, and 8 divides 16 twice. Thus, the cube root of 16 is the product of the cube root of 8 and the cube root of 2. Evaluate the perfect cubes. The cube root of 27 is 3. The cube root of 8 is 2. 2 times 3 is 6. Thus, we have 6 cube roots of 2. 12 times 2 is 24, giving us 24 cube roots of 2. So for each of our two terms here, we do have radical terms, but each of our radicals has the same exact radicand and the same index or root of 3. Thus, like radicand, like index, we can combine the two terms. 6 plus 24 gives us 30. So we have 30 cube roots of 2. We know we're fully simplified because we cannot further simplify the cube root of 2. 30 cube roots of 2. For the following exercises 28 through 32, combine the radical expressions if possible. For number 28, we have 7 square roots of 2a minus 3 minus 4 square roots of 2a minus 3. See here that for each of the two terms, our radicand is 2a minus 3, and they are each under the square root. So these are like radicands. We can combine the coefficients, 7 minus 4, which gives us 3. For number 28, we have 3 square roots of 2a minus 3. For number 29, however, the square root of 25y plus the square root of 64y, our radicands here are not the same. For each of the two terms, we will use our product rule to further simplify our radical expression. Go into the full view here. For the square root of 25 times y, isolating the factor of 25 under its own radical, multiply the factor of y under its own radical. Square root of 25y plus the square root of 64y, taking the factor of 64 and the factor of y, placing it under their own radicals, and multiplying. That is our product rule for radical expressions. Evaluate the perfect squares. Square root of 25 is 5. We have here 5 square roots of y. What about over here? The square root of 64 is 8. Here we have 8 square roots of y. Overall, how many square roots of y do we have? Because these are like radicals, same root of 2, same radicand of y. 5 plus 8 is 13. We have 13 square roots of y. Y cannot be factored. Y is one variable to one exponent. Thus, it is fully simplified. For number 30, the cube root of 16t to the fourth power minus the cube root of 54t to the fourth power. Immediately we're thinking we have both coefficients and variables under the radical. So just like we saw for 29, the 25 multiply y, we placed each factor under its own radical. For number 30, we're going to do the same thing. We're going to take 16, place it under its own cube root, and t to the fourth power and place it under its own cube root. Minus the cube root of 54. Multiply the cube root of t to the fourth power. Using the product rule for radicals for each of our two terms. 16 is not a perfect cube. Just in the last example, we saw, and you're going to see that just this repetitiveness here, the cube root of 16, 8 times 2 is 16. Thus, the cube root of 8, multiply the cube root of 2, where the cube root of 8 is 2. So again, where are we getting the 2 cube roots of 2? This 2 right here is the cube root of 8. And the cube root of 8 times the cube root of 2 is the cube root of 16. What do we have going on right here? T to the fourth power is under the cube root. Remember our shorthand rule? The exponent is 4. The root is 3. How many times does 3 go into 4? 4 divided by 3 is 1 with a remainder of 1. 3 goes into 4 once with 1 left over. What does this mean? This means that for the cube root of t to the fourth power, we are going to factor out 1 factor of t from underneath this radical. What does the remainder of 1 mean? 1 factor of t will remain underneath the radical. This is because t to the fourth power is the product of t cubed and t. And these factors here underneath the cube root radical, you see simplifies. The cube root of t cubed, our inverse property, cancels the cube root and the power of 3 because they cancel one another. If you raise something to the third power and then take the cube root, you are canceling those operations, leaving you with your original factor of t. T multiply the cube root of t, well, that's what we have right here. 1 with the remainder of 1. We're going to get right here as well. The cube root of t to the fourth power is t. Multiply the cube root of t. That's going to be every time. However, what is the cube root of 54? 54 is the product of 27 and 2. Under the cube root of 27 is 3, because 3 to the power of 3 is 27. Right, we just rewrote 27 as 3 cubed. However, 3 cubed, which is 27, under the cube root, cancels. And of course, leaving us with 3 because we know the cube root of 27 is 3. So let's clean this up and see if we can simplify further. We have 4 factors here. The 2 and the t we will move out front. The cube root of 2, the cube root of t cannot be further factored or simplified, so we combine them together. 3 and t out front. Combining, again, this is multiplication, right? The cube root of 2, multiply the cube root of t. Using the product rule for radicals is the cube root of 2t. Now you see here for each of these two terms, our radicand is the same, our root is the same. Can we combine these coefficients? Will these allow us to combine 2t minus 3t? Well, just using our rules for combining polynomial expressions, 2t minus 3t, 2 minus 3t is minus 1t. However, we are multiplying that to the radical expression, cube root of 2t. So notice here how these two terms combine down to 1 because 2t minus 3t is minus 1t. Multiply our common factor of cube root of 2t. And now normally we don't write the minus 1 coefficient, so we would just leave this as minus t times the cube root of 2t. For number 31, 10 cube roots of z minus the cube root of z to the 4th power. For number 31, the first term here has a radicand of z. Z is understood to be to the 1st power. There is only one factor of z under our cube root for 10 cube roots of z. So we cannot further simplify because in order to further simplify, we need to find a factor that is a perfect 3rd power. For z, z is to the power of 1. So there is only one factor for z, and that's z itself. However, for the minus cube root of z to the 4th power, z to the 4th power, we have 4 factors of z. We can rewrite z to the 4th power as z cubed minus z. Z to the 3rd power multiplies z to the 1st power because, of course, the exponents 3 plus 1 give us the 4. Let's think about that there. The cube root of z to the 4th power, using our product rule for radicals, the cube root of z cubed multiply the cube root of z. Using our inverse property, z to the 3rd power under the cube root leaves us the factor of z. Just as we saw in the last example, going back to the PowerPoint, look at number 30. We had t to the 4th power under the cube root. It's no different here. We just changed the variable. Z to the 4th power under the cube root, just like t to the 4th power under the cube root, 1 with a remainder of 1. We are going to factor out one factor of the z and leave behind one factor of z, just like we did with the t to the 4th power under the cube root. First term here, we can't do anything to it. So here we have 10 cube roots of z minus z cube roots of z. For each of these two terms here, we have a radical with the radicand of z, and the root is 3. These are like radicals, so we can combine their coefficients. How many cube roots of z do we have? We have 10 minus z. And this is significant to show here because 10 and z cannot be combined. Think of it in that question. How many cube roots of z do you have? Well, I had 10, but I took away z of them. Well, z is a variable. We don't know how much z is. So I can't do a subtraction here. This isn't 7, right? 10 minus z isn't 7. 10 minus 3 is 7. We don't know that z is 3. So in this case here, we have to leave it as the binomial 10 minus z. We do want to combine the two because we do want to show that these are in fact like radicals. Cube root of z, cube root of z. How many? We have 10 minus z cube roots of z. And for number 32, 5 cube roots of 24u squared plus 2 cube roots of 81u to the 5th power. For the first term, I have 5 multiply the cube root radical. With that cube root radical, we will use a product rule for radical expressions. The 24 is multiplying the u squared. So let's take the 24 and place it under its own radical, and the u squared, place it under its own radical. Similar to our second term, plus 2. Multiply the cube root of 81 u to the 5th. 81 is multiplying u to the 5th, so we'll place 81 under its own radical. And u to the 5th will go under its own radical. And of course, that is the cube root radical. Moving left to right here, the cube root of 24. 24 is not a perfect cube. However, it's between 8 and 27. 8 and 27 are the perfect cubes that we work with. 8 is 2 cubed. 27 is 3 cubed. 8 divides 24 3 times. As we see here, using our product rule for radicals, cube root of 8 multiply cube root of 3. Now what about our variable here? The cube root of u squared. U squared means we have 2 factors of u. 2 factors of u under the cube root. Well, in order to simplify any factor out of that radicand, we must have a factor to the power of 3. Some factor to the power of 3. Well, we only have 2 factors of u, so we cannot simplify the cube root of u squared. Because our exponent is smaller than our root of 3, this tells us that we cannot simplify out any perfect cube factors from our radicand. It stays as the cube root of u squared. (81) under the cube root. 81 is not a perfect cube. It is between 64 and 125. 64 is 4 cubed. 125 is 5 cubed. 81 contains a perfect cube factor of 27. 27 divides 81 3 times. For the cube root of u to the 5th power, note that our exponent is larger than our root of 3, so we can factor something out from under this radical. Think about the shorthand rule. Divide the exponent by the root. 5 divided by 3 is 1 with a remainder of 2. In other words, 3 will go into 5 once and have 2 left over. What does that mean for the factors? We will factor out 1 factor of u. The remainder of 2 says we will leave behind 2 factors of u. 2 factors of u is u squared. For our first term here, we're multiplying these 4 factors, but we're going to simplify the perfect cubes. The cube root of 8 is 2. The cube root of 27 is 3. 5 multiplied 2 is 10. The cube root of 3 multiply the cube root of u squared. Because we cannot further simplify these radicals, we will bring them together into one radical using the product rule. That is the product rule for radical expressions. 2 times 3 is 6. Our factor of u, we will pull out next to the 6. Cube root of 3 multiply cube root of u squared gives us our cube root of 3u squared. So we have 10 cube roots of 3u squared added to 6u cube roots of 3u squared. For our 2 terms, they are like radicals. They have the same root of 3. They have the same radicand of 3u squared. Thus, combining the 2 terms by combining their coefficients, 10 plus 6u. This is how many radicals we have. For our cube root of 3u squared, we have 10 plus 6u times the cube root of 3u squared, or we can say we have 10 plus 6u cube roots of 3u squared. For number 40, each of our radicands are binomials. We have a polynomial or a binomial 9x minus 9 under our square root. We have a radicand of x cubed minus x squared under our square root. For each of these binomials, for these polynomials, the first thing we want to consider here, if we are to find a factor underneath our radical, to factor out of the radical, well, we need to factor the polynomials. To factor 9x minus 9, we consider, is there a greatest common factor for 9x minus 9? And we see there is a 9 in each of the two terms. That is a factor of 9. So underneath the radical, we will factor out a 9. So under our square root, we have 9x minus 9. Factoring out a 9, we have 9 and the product of x minus 1. 9 times x is 9x. 9 times the minus 1 is the minus 9. For x to the third power, subtract x to the second power. Is there a greatest common factor for this binomial? Each of these two terms share two factors of x. So we factor out an x squared under the radical. Factoring out an x squared, we leave behind x minus 1. We confirm this. X squared times x is x cubed. X squared times a minus 1 is a minus x squared. For number 40 here, we'll go to the full view. We have a factor of 9 and x minus 1. They're multiplying each other. Our product rule for radicals, square root of 9 is multiplying the square root of x minus 1. And now these are two terms under the radical. These are not factors. Our product rule is exactly that. It allows us to use things that are multiplying. The 9 is, through factorization, the 9 is multiplying the x minus 1. Thus, we have a factor of 9 and a factor of x minus 1. If this x minus 1 could be further factored by some GCF or some other technique, we would consider. But for here, x minus 1 cannot be further factored. It's prime. And we're done there. However, we evaluate the square root of 9, and we get 3. How many square roots of x minus 1 do we have? We have 3 square roots of x minus 1. But we're going to subtract something. What is that we subtract? With a factor of x squared and a factor of x minus 1, our product rule, square root of x squared multiplied the square root of x minus 1. Inverse property, square root of x squared is x. Note here for each of these two terms, we have radicals with our radicand x minus 1 under the square root sign. So this is a root understood to be 2. The root is the same, the radicand is the same, thus these are like radicals. We combine their coefficients, 3 minus x. How many square roots of x minus 1 do we have? We have 3 minus x square roots of x minus 1. Another way to say this, 3 minus x multiply the square root of x minus 1. Exercise 41, we have 2 cube roots of a to the fourth power times b to the second power plus 3a cube roots of a multiply b to the second power. For each of our two terms here, we have radical expressions under the cube root. A to the fourth power multiply b squared. For each of these two factors, we will place them under their own cube root. Likewise, for the second term, a multiply b squared, we will take each of these factors and place them under their own cube root. And with the first term here, exponent is larger than the root, so we will be able to factor out some perfect third power. A to the fourth, as we've seen with previous examples, power of 4, root of 3, a to the fourth power is a cubed multiply a, thus that a cubed factor under the cube root is going to get factored out to be a. In other words, 4 divided by 3 is 1 with a remainder of 1. We factor out a factor of a, we leave behind a factor of a. A multiply the cube root of a. Just like we saw the cube root of t to the fourth, the cube root of u to the fourth, you factor out one factor, you leave behind one factor. Our exponent is smaller than the root. In other words, we do not have 3 factors of b that can be factored out. The cube root of b squared is fully simplified. Our factor of 3 and a is simplified. Our job here is to look at the remaining radical factors. The cube root of a, this is one factor of a. We cannot simplify by factoring out three factors because there's only one factor of a. Cube root of a is fully simplified. For the last factor, cube root of b squared contains two factors of b. In order to factor out of the cube root, we must have some factor to the power of 3. We can't do that. Cube root of b squared is simplified. Now, to simplify the entire term, because we cannot simplify these two radicals on their own, we will now bring them together using our product rule for radicals. Here, 2a times the cube root of ab squared plus 3a times the cube root of ab squared. Now, are these like radicals? Root or index of 3? Likewise, their radicands are exactly the same, ab squared. Thus, we combine their coefficients, 2a plus 3a. And when we look at those coefficients a little bit closer, 2a plus 3a, these are actually like terms. How many a's do we have? Well, 2 plus 3 says we have 5 a's. Here, 5 multiply a, multiply the cube root of ab squared. Exercise 43, the square root of 4r to the 7th power s to the 5th power plus 3r squared times the square root of r to the 3rd power s to the 5th power minus 2rs times the square root of r to the 5th power s to the 3rd power. For each of these terms here, we will use our product rule for radicals. For each of the factors, we would place them under their own square root sign. Evaluating any perfect squares that we may have, the square root of 4 is 2. And now for the square root of r to the 7th power, again, understanding that our root is a 2, right? Using the shorthand notation, 7 divided by 2. Well, how many times does 2 go into 7? 3 times, with a remainder of 1. For a 3 remainder of 1, this means to factor out 3 factors of r. The remainder of 1 tells us to leave behind a factor of r. To understand this, r to the 7th power can be rewritten as r to the 6th power times r. Using our product rule for radicals, the square root of r to the 6th power, multiply the square root of r. Well, what here can you square in order to get r to the 6th power? If you square r cubed, squaring r cubed is r cubed multiply r cubed. 3 factors of r multiply 3 factors of r, which in total is 6 factors of r to the 6th factor. Thus, square root of r to the 6th is r cubed with a factor of square root of r. 7 divided by 2 is 3 with a remainder of 1 factor under the radical. Use this for the square root of s to the 5th power. 5 divided by 2 is 2 with a remainder of 1. Factor out 2 factors of s, leave behind 1 factor of s. Plus 3r squared. For the square root of r cubed, again, r cubed is r squared times r. The r squared under the square root becomes r. 1 factor of r gets left behind under its radical. Again, why is this? 3 divided by the 2, which is our root. 3 divided by 2 is 1 with the remainder of 1. The 1 tells you to factor out an r. The remainder of 1 says leave behind a factor in r. Square root of s to the 5th power, 5 divided by 2, just as we saw over here, square root of s to the 5th, s squared multiply the square root of s. Minus, I'm running out of space here, so I'm going to go below, minus 2rs, square root of r to the 5th power, just use the same concept for the square root of s to the 5th power. The square root of r to the 5th power, r squared multiply the square root of r. For the square root of s cubed, we're going to use the same rule for the square root of r cubed. Here we got r multiply the square root of r. Here we're going to get s multiply the square root of s. So now we need to clean up our simplification here. For our first term, everything that gets factored out of the radical move out front. 2r cubed s squared. For the first term here, the square root of r multiply the square root of s. Using our product rule for radicals, bringing those two factors together, the square root of rs. Plus our second term, 3 multiply r squared, multiply r, well this is r cubed, and this factor of s squared is also outside of the radical. Our factor, square root of r, square root of s, multiply those two together for the product rule of radicals, the square root of r times s, minus 2 r times s times r squared times s. So notice here there's 3 factors of r and 2 factors of s. And our remaining factors are radicals, the square root of r times the square root of s, which is the square root of rs. For those 3 terms for number 43. For number 43 there, this simplifies down to our following 3 terms here. Now note for our 3 terms, they all contain a radical under the square root r times s. So all 3 of these terms are like radicals. Therefore, we can combine their coefficients. 2r cubed s squared plus 3r cubed s squared minus 2r cubed s squared. Well, wouldn't you know that? All the coefficients are also like coefficients. In other words, all 3 of these terms can actually combine down into one single term. Notice here, if I just hide that minus sign there, this term here and this term here, they're exactly the same. 2r cubed s squared multiply the square root of rs. I throw a minus sign in the front, that's the opposite. They're the same, now they're opposites of one another. What do we know about opposites when we combine them using addition? 8 and negative 8 combine to give us 0. 15 and negative 15 combine to give us 0. Here, any number and its opposite, these two are going to combine to give us 0. In other words, they cancel out. What are we left with? A positive 3 times r cubed times s squared times the square root of rs. And that is our simplified expression for number 43. For number 49, simplify the following expression, square root of 32 plus the square root of 1/2. Now keep in mind, when we simplify radical expressions, our radical must not contain a perfect nth power factor. Here, working with the square root, we cannot have a factor under the radical that's a perfect square. So for 32, rewriting it as 16 times 2, where the factor of 16 is a perfect square factor. For the square root of 1/2, a simplified radical expression does not contain a factor under the radical, nor does it contain a radical in the denominator. So for our second term, using the quotient rule to rewrite this as the square root of 1 divided by the square root of 2, we will now simplify some perfect squares. The square root of 16 is 4. So we get 4 square roots of 2. But we are going to add this. Well, the square root of 1 is 1. So we're going to add this to 1 over the square root of 2. But we cannot have a denominator with a radical. What do we do when we have a radical in our denominator? We rationalize the denominator. For the square root of 2, we can get rid of that radical by multiplying it by itself. In other words, if we multiply the numerator and denominator of our fraction by the square root of 2, then what we've done is we've multiplied this fraction by an understood value of 1. Any number divided by itself is 1, and it's not going to change our expression, its value, it's just going to change the way it looks. In the numerator, 1 multiply the square root of 2 will give us back the square root of 2. We will divide this by the square root of 2 times the square root of 2, which is the square root of 4, which is 2. The square root of 2 divided by 2, if we want to write this in terms of the square root of 2, how many square roots of 2 do we have? Well, we have 1, but we're dividing it by 2. So how many square roots of 2 do we have? We have a half of a square root of 2. In other words, taking that 1 here and that 2 and writing it as a fraction, multiply the square root of 2. So now, how many square roots of 2? I have 4, but I'm going to add a half. 4 and a half square roots of 2. If I want to write 4 and a half as a fraction, 4.5, that is 9 halves. I have 9 halves square root of 2, or I have 4 and a half square roots of 2.